Today we're going to look at a certain take on the notion of primes within a certain set of matrices. And this comes from a paper from Math Magazine in 1986 by Rivet and McKinnon, and it's called Prime Matrices. And so in particular, we'll consider the following set of matrices. I'll call that set M, and it'll be equal to all 2 by 2 matrices with non-negative integer entries where the determinant is equal to 1. And then our goal is to determine what the primes are from this set. So I'd like to point out that generally in number theory, there are 3 types of numbers. There are units, primes, and composites. And so units are elements with multiplicative inverses. And this is essentially why we don't consider the number 1 a prime within the natural numbers, because it has a multiplicative inverse itself. And then we have primes, and primes satisfy the following rule. And this is simplified a little bit to the case where our only unit is 1. But that being said, it could be rewritten in a more general case. So just keep that in mind. So anyway, primes satisfy this rule. If we can write P as A times B, then A is equal to 1 and B is equal to P, or A is equal to P and B is equal to 1. In other words, the only factorization of a prime is as that prime times 1. And then there are, of course, composites, which are neither units nor primes. Okay, so maybe the first question we might ask is, what are the units inside of M? Okay, well, let's suppose that we have A, which is equal to A, B, C, D, and it's inside M and a unit. So that means it has a multiplicative inverse inside of M. Now, of course, if we extend the set we're looking at, lots of things have multiplicative inverses. In fact, everything inside of M has a multiplicative inverse because it has non-zero determinant. That being said, we want to look at things that have inverses which are inside of this set. Okay, so that means that the inverse of this must be inside of M. But let's recall that the inverse is equal to 1 over the determinant. The determinant is 1 in this case, and then the rule for finding the inverse is to swap the diagonals, so we would have dA, and negate the off diagonals. Okay, great. So now let's notice immediately we know that B and negative B are bigger than or equal to 0, and C and negative C are bigger than or equal to 0. Given that they're in this set, that might look like B1 minus B, but it's really B comma negative B. Okay, so if B and negative B are both non-negative integers, and C and negative C are both non-negative integers, so that means that immediately we know that B equals C equals 0. So in other words, we have a diagonal matrix. Okay, so now let's take this product. So we know A times A inverse must be equal to the identity matrix. So let's put the identity matrix over here. But then by what we've just calculated, we know that A has the form A00D, and thus A inverse has the form D00A. But now taking that product, we get the diagonal matrix, which is built with just AD on the diagonal. But that means that AD is equal to 1, but that only occurs if A equals D equals 1, which implies that A is in fact equal to the identity matrix. So that means the only unit inside of M is in fact the identity matrix. Okay, so now that we've looked at the units here, let's explore some of the primes. Okay, now let's look at the primes in M. And I'll just start with the following observation. Let's observe that P, which is equal to 1, 1, 0, 1, and then the transpose of P, which is Q, which is 1, 0, 1, 1, are both primes inside of M. And we'll prove this by trying to factor one of them and show that our factorization fails. Okay, so let's do that. So let's suppose that we have P is equal to A times B, where A and B are inside of M. But then let's give A and B some form. So let's maybe write this out. So we have P is that form, and then we'll say that A is A, B, C, D, and maybe B is X, Y, Z, W. Okay, nice. But now let's multiply these up and notice that we'll get AX plus BZ, so that's in the first entry. In that second entry, we get AY plus BW. In that third entry, we'll have CX plus DZ. And then in that fourth entry, we'll have CY plus DW. And that's just by standard rules for matrix multiplication. In fact, I made a video on why matrix multiplication is the way it is that explains why we have this weird multiplication rule. So that should be in a card right now and also linked at the end of the video and in the description if you'd like to check it out. I'm really happy with how that video went. Okay, so anyway, now we have the following setup, but that gives us a system of equations. Notice we have AX plus BZ is equal to the number 1. We have AY plus BW is also equal to the number 1. We have CX plus DZ is equal to the number 0. And then finally, we have, let's see, this was CY. CY plus DW is equal to the number 1. And now we just play some games with this. So notice the fact that CX plus DZ equals 0 means C is 0 or X is 0, and D is 0 or Z is 0. So let's just maybe take the case that C equals 0. So definitely that's one of the cases. The other case would be X would have to be 0. Okay, but now plugging that into this equation, notice that means that Y is really allowed to be anything at the moment because we've got a 0 here. But it also means that D times W must be equal to 1 because this collapses to 0. But if D times W equals 1, that means that D equals W equals 1. So that's what we get after this first round of simplification. Oh, but now notice since D is equal to 1, back up here, we see that Z must be equal to 0. So we've got Z is equal to 0. Okay, so we've determined 4 of our variables. So let's maybe plug those into the remaining equations and see what that leaves us with. Okay, so Z equals 0 plugged up here gives us AX equals 1. And then let's see, W equals 1 up here gives us AY plus B times 1, which is B equals 1. Okay, and then notice that we've taken care of this. We have C is 0 and D is 0, so there's no more information from here. Also, we've used this extensively as well, so there's no information from here either. Okay, good. But now let's see where we can go from here. So since A times X is equal to 1, that immediately tells us that A is equal to 1 and X is also equal to 1. And now throwing that down here, we'll see that we now arrive at the equation Y plus B is equal to 1. So that means we have Y is equal to 0 and B is equal to 1, or Y is equal to 1 and B is equal to 0. Those are our two possibilities there. Again, we're working over the natural numbers here. So let's look at this one. So if Y is equal to 0 and B is equal to 1, let's plug that up here to see what we have. So that means that this matrix turns into 1, 1, 0, 1, whereas this matrix right here turns into 1, 0, 0, 1. So the only possible factorization is the one that includes the identity matrix. And then likewise, for this one over here, we'll get essentially the same thing, but just with that product reversed. Okay, so anyway, let's review what we've just done. We took our matrix P and we tried to factor it, and we showed that the only possible factorization included the identity matrix. But that's exactly what it takes for this to be prime. And then through a very, very similar argument, Q will also be prime. And in fact, now we'll show that P and Q are the only primes. So on the last board, we showed that this matrix P, 1, 1, 0, 1, and this matrix Q, which was its transpose, were prime in our set of matrices M. And now we'll prove that these are in fact the only primes. And we're going to do this, well, using the strategy from this paper, which I think is pretty interesting. And that is, we'll show that every matrix except for the identity must be a multiple of P or Q. And we'll do this by taking a matrix which is not a multiple of P or Q and showing that that matrix must be the identity. Okay, so let's do that. So let's take an A in M such that A is not a multiple of P and not a multiple of Q. Then, like I said, our goal is to show that A is the identity. That'll prove this statement. Okay, so now let's introduce some notation for A. So we'll set A equal to the matrix A, B, C, D. And notice that our assumption is that A is not equal to X times P, and A is not equal to Y times P for all X and Y in M. So in other words, if we let X and Y range over all of M and multiply it into P or Q, we never get A. Okay, good. So let's see how we might do this. Well, let's notice that this statement right here is equivalent to the following statement. We have A P inverse and A Q inverse are not elements of M. Because if they were, well, then we could solve this equation and we would have an equality there, not a not equality. Okay, good. So, well, we can calculate P inverse and Q inverse fairly easily. Notice that P inverse is equal to 1 minus 1, 0, 1, whereas Q inverse is equal to 1, 0, minus 1, 0. In fact, these matrices P and Q have the interesting property that they encode addition into matrix multiplication. I'll let you think about that, but I give that exercise in my abstract algebra class quite commonly. Okay, so now let's rewrite this with our matrix A and those forms for P inverse and Q inverse. Okay, so we know that A, B, C, D times 1, negative 1, 0, 1, which is equal to, let's do the calculation. So we have A, and then here will be B minus A, and then here will be C, and then in this entry right here will be D minus C. We know that this is not inside of M. And simultaneously, we know that the other product, A, B, C, D times 1, 0, negative 1, 0, which is equal to, let's see, this will be A minus B, B, C minus D, D is also not an element of M. But notice that both of these matrices over here by construction have determinant 1. That's because since A is in M, it has determinant 1. But P and P inverse both also have determinant 1, so their product has determinant 1. So that means the only thing that can go wrong for these being inside of M is if they have negative entries. Okay, so let's point that out. So the fact that these are not inside of M gives us two conditions. We know that B minus A is less than 0, or D minus C is less than 0. That's what it takes for this to be not inside of M. And we know that A minus B is less than 0 or C minus D is less than 0. That's what it takes for this matrix to be outside of M, because that means it would have negative entries, but M doesn't have matrices with negative entries. Okay, well, let's notice that a couple of these things cannot occur at the same time. Notice that B minus A can't be less than 0 while A minus B is less than 0, and likewise for the D minus C and the C minus D. So that, in fact, boils this down to two conditions. We know that B minus A is less than 0 and C minus D is less than 0. So that would be taking this diagonal right here. Or we know that the other diagonal must occur. That other diagonal is A minus B is less than 0 or D minus C is less than 0. And now let's maybe work off of this first one, and working off the second one will be really similar, and I'll leave this one as a homework. So in other words, we're kind of considering these two cases individually. Okay, so if B minus A is less than 0, that means that A minus B has to be bigger than or equal to 1. And likewise, if C minus D is less than 0, that means that D minus C has to be bigger than or equal to 1. Like that. Oh, but let's notice that that means that A has to be bigger than or equal to B plus 1, and D has to be bigger than or equal to C plus 1. Oh, but now we can take this product and we get AD is bigger than or equal to B plus 1 times C plus 1. Okay, so that's looking good. But then also, we know that our original matrix up here had determinant 1, which means that AD minus BC is in fact equal to 1, which can be used to write AD as BC plus 1. Okay, so now let's put these two little pieces of information together. Okay, so we've got AD must be bigger than or equal to B plus 1 times C plus 1, but we can multiply that out to BC plus 1 plus B plus C. Oh, but notice that AD is the same thing as BC plus 1. So I'll underline that here and here. But we've got this BC plus 1 over here on the right-hand side as well, so those can cancel. So that gives us the equation 0 is bigger than or equal to B plus C. Okay, but let's look over here. M is made up of things from non-negative integers. So the only way for B plus C to be less than or equal to 0 is for both of them to be equal to 0. So we get B equals C equals 0. Oh, but that means our matrix was diagonal, but using similar strategies to what we saw before, that means that A and D both have to be 1 because the determinant has to be 1. So putting that all together, including those words that I said, we have A is in fact equal to the identity matrix. Okay, so let's reiterate what we did. We supposed that A was not a multiple of P and it was not a multiple of Q, and we showed that A had to be the identity matrix. So what that means is that every other matrix is a multiple of P or Q, which tells us that every other matrix can be completely factored into factors of P and Q. So let's summarize that on the next board. Okay, so here's a nice summary of what we've seen. So let's notice that if we take any A, B, C, D in M, so that's one of the matrices inside of M, then if D is less than C and B is bigger than A, we can perform the following factorization. So A, B, C, D can factor as A, B minus A, C, D minus C times this matrix, which was P. And this inequality-like setup is required so that these are still positive, which lands inside of M. I guess I should say that these can be non-strict inequalities all around, because that'll still land inside of M. And then we've got 3 more similar cases. So let's maybe skip this one. You could read it if you want. Go to the third. If A is bigger than or equal to B and C is bigger than or equal to D, then we can factor our matrix as A minus B, B, C minus D, D times our matrix Q. And then you've got this one more, which is multiplication by Q from the right, whereas this one is multiplication by P from the right. So we've got those 4 brands of factorization. That's like factoring a P out of the right, out of the left, Q out of the right, or out of the left. And then here's something that is super important. And each time you perform one of these factorizations, the total sum of the matrix entries decreases. So notice here the total sum of the matrix entries is A plus B plus C plus D. Whereas here it's simply, let's see, B plus D. So that decreased. And we know that it decreased because A and C both cannot be 0, because then you would have a non-invertible matrix. But the fact that that decreased means that there is some end to the factorization, because each time you perform a factorization, you get some decreasing setup. And then I guess the minimum total sum would be 2. So eventually, you'll get down to 2. Okay, so anyway, what that tells us is that A, any matrix inside of M, can be factored as follows. We've got P to the N1, Q to the M1, P to the N2, Q to the M2, all the way up P to the NK, Q to the MK. And here N1 and or MK could be equal to 0 just as necessary, because your factorization could begin with a P or a Q and end with a P or a Q. And that allowance of 0 allows us for that. That being said, all of the middle terms have exponents which are bigger than or equal to 1. Okay, so now that we've seen that, let's look at an example factorization. So let's finish this video with the following example factorization. So we've got the matrix 3, 5, 1, 2. Notice this has determinant 1 because 3 times 2 is 6, minus 5 is 1. So we've got those factorization rules on the last board, and we'll apply those. So the first thing that we'll notice is we can factor a P out of the left-hand side. Recall that P was the matrix 1, 1, 0, 1. And then applying those factorization rules leaves us with a 2, 3, and then a 1, 2. Great. So notice if we were to take the product of those 2 matrices, we would get back exactly where we started, and that's what we want. Okay, and next up we would like to maybe factor what's left over. So I'll maybe underline this in green right here. Okay, so again, applying those factorization rules that we had on the last board, we'll see that we can factor that as the following product. So I'll leave this P out front, and in this case, I'll take a P out of the right-hand side. And that'll leave me with 2, 1, 1, 1, and then 1, 1, 0, 1. Okay, so that's how we performed this factorization. So those are equal. Okay, so now let's see what we're left with. We're left with this thing right here. And then all we have to do is factor that and see where we go from there. Okay, so again, applying those factorization rules, we'll see that that blue underlined stuff will factor as 1, 1, 0, 1 times 1, 0, 1, 1. Okay. So let's complete this just by bringing that down. And then let's color code this. So this is our factorization from above. So here you could either view that as factoring a P out of the left-hand side or a Q out of the right-hand side. And then you just happen to get a P or a Q left over. But now notice, like I just alluded to, those are all of our primes. This is P times Q times P. So if I were to rewrite that as my prime matrices, I've got P squared Q times P, and I've completed the factorization of this matrix into primes. So now maybe I'll leave a little bit of a homework exercise for you, and that is to factor the following matrix. Let's say maybe we've got 7 on the diagonals, and then here we'll have like maybe an 8 times a 6. So that's definitely inside of M because its determinant is 49 minus 48, which is 1. So let's maybe try to factor that into products of our prime matrices P and Q. And let's recall that I mentioned that video where I explain why matrix multiplication is the way it is. That should be on the screen right now if you'd like to check it out. And that's a good place to stop. Thanks for watching and sticking around until the end of the video. And since you're here, don't forget to gently press that like button, subscribe, ring the bell, and select all notifications to never miss a video. If you want to get your name in the credits like you see here, access the live seminar series, review videos before release, and more, go to patreon.com/michaelpennmath and become a Patreon member today. If you want full ad-free course content, subscribe to my second channel, Math Major. I've got courses on linear algebra, complex analysis, and proofwriting, among several others. And that's everything. Bye.